Hey, Chemistry 11. So today we're going to cover the topic of excess and limiting reagents. So far you've been looking at stoichiometry, you've been looking at the idea that you can actually make statements about how much of one reactant you'll need to completely react with another. Given a balanced chemical equation, you've been able to make statements about how much of a mass or a volume or even number of particles you might need to have two reactants completely balance each other out and make a product. So, and you also, of course, last day looked at molarity, so examined using molarity in stoichiometry. I told you that it's all about that a good analytical chemist would be someone who is also going to be a good cook because they understand the importance of adding the appropriate number of different ingredients together within any kind of recipe, which itself is a chemical reaction. Recipes have lots of chemical reactions in them. But that being said, sometimes you don't truly want to balance the equation in terms of, well, I shouldn't say that. Sometimes you don't truly want to balance the reactants perfectly to each other. In other words, you might want to add a little bit extra of one reactant in comparison with another, more than you need to completely consume that reactant. And this is where we're getting into this whole topic of limiting and excess reactants. We've written on the board here just as background or notes, also available in your readings or similar information. Readings start on page 132 of your text. Often it's desirable, or it's often going to be inevitable, that one or more reactants is present in some kind of an extra amount. These are called excess reactants. Some sources will say reagents, excess reactants. It's the same thing. When there are excess reactants, this means that by definition, there's also going to be limiting reactants. So the limiting reactants are those reactants that get entirely consumed up. Because they all get used up, it's the amount of the limiting reactants that determines how much product you can make. It doesn't matter how much of one reactant you add. If you only add a little bit of the other reactant, then you're going to have a whole bunch of one of the reactants left over and a little bit of the product. So sometimes this is actually a desirable thing. For example, sometimes one of your reactants might be hazardous to health or to the environment, and you don't want to have any of that reactant left over, whereas possibly your other reactant, you can dispose of it very easily, or it's not harmful in the first place. So these are considerations that people might have when they're actually running an experiment to make a certain amount of a product. Do they want to have an excess reactant? If so, which one would they want to have in excess? Or maybe they want to perfectly balance things out. If you were working with, say, making sodium chloride table salt by combining sodium and chlorine, both of those are hazardous chemicals. So you would want your reactants to be as stoichiometric balanced as possible, versus sometimes others you don't want to do that. You want to use up one and have some left over of another. We're going to start by looking at one. It's a lot more interesting, honestly, than just talking about these. So I'm going to bring out some reactants for a reaction that you might have seen before. Here's what I've got. This right here is hydrochloric acid at 1 molar concentration. I'm going to add a little bit of pH indicator to it. This is actually a mixture of different pH indicators, so it doesn't have just one color change, it has a number of different color changes. Oh, there we go. Bottle's kind of broken. All right, so we see here we've got a color change. It came out kind of blue-green and it ends up red. Typically, for your pH indicators, your red color is taken to mean that you have an acid. So here we have an acid here. It's indicating hydrochloric acid. Hasn't entirely mixed, but that doesn't matter. This is calcium carbonate right here. It's obviously an ionic compound, solid. If I were to mix this into water, one thing I would expect as an observation would be the water be very cloudy. Carbonate salts are often quite insoluble. Calcium carbonate is an example of a very insoluble salt. Chemically, calcium carbonate is the same thing as limestone. And we know that limestone is only very slightly soluble in water, which explains why it can make caves. So I'm going to add the two of them together, but let's examine the chemical reaction first, not bump over my acid. Here's the balanced chemical equation. So we see up here across the top, in the middle there, we have calcium carbonate being reacted with hydrochloric acid. Do note that we have a coefficient of 2 on the HCl, creating calcium chloride, water, and carbon dioxide gas. So there's going to be all sorts of interesting things going on here. We're expecting maybe there will be a color change. I haven't actually done this reaction with the indicator, so I don't know, but I think there will be a color change. And we're expecting also to be a release of a gas. So there's going to be a whole lot of neat stuff going on here. That's why I chose it. First of all, let's get our acid into the Erlenmeyer flask. All right. Now, because the water is not a reactant at all, I'm actually going to rinse this out a little bit because, after all, I don't want to have acid left over in this cylinder. And I can do that, and it won't affect any of the outcome of the reaction. The only thing I'm also going to do kind of on the fly a bit right now is add a little bit more indicator. Indicators themselves are actually very weak acids, but extremely weak, and they're in very small amounts, so we shouldn't expect it to have much of an effect on the outcome of the reaction itself. They're just useful because they tell you if there's been a pH change. Oh, this is a lot nicer, you see here. So we have a nice red color that we expect when there is an acid present with the universal indicator. So now I have a dry funnel. Don't want this stuff to get stuck in it. And I'm going to add this to the calcium carbonate, to the hydrochloric acid. I'm going to do the same thing. I'm going to rinse this with water too. A little bit of the calcium carbonate got stuck to the side of the funnel. That's better. There's a lot going on here. So we see a dramatic release of a gas. Another thing you can see is that the mixture is actually quite cloudy. Remember, it started out as a clear liquid. I added the acid to it. It gave it a color, but it was still transparent. I have washed this around here. We've got, is there much of a color change? I don't know if there's much of one yet, but I'm going to be patient. We're going to wait on that. One thing you might notice is that it appears that the color is a little bit more towards the orange at the top of those bubbles. I'm going to keep mixing this around a little bit. Oh yeah. You can probably kind of hear that a little bit. So maybe a very slight color change, but especially with those bubbles. But one thing we can tell already is it's very clear that there has been a chemical reaction with the release of all this gas. There. But the other thing, and this is particularly important for the purposes of today's lesson, is that, switched out the camera by mistake, no matter how much I mix this around, the solution is staying cloudy. My prediction based on what I know is that it's going to stay cloudy, and that's not going to shift no matter how long I let this sit. We'll let it sit for a while. It's starting to clarify a little bit. A reminder though, calcium carbonate is not soluble. Calcium chloride is soluble. Good. So let's examine what went on there. So I added 4 grams of the calcium carbonate, and I added 50 milliliters of 1 molar hydrochloric acid. I purposefully planned that reaction so I was adding some extra of one of the reactants. And the question becomes, all right, which one was I adding extra of, and do we have any evidence that that was the case? When you are looking at problems involving excess reactants, you start, like you always start with stoichiometry problems, by calculating chemical amounts given the information that you're provided with. Here's the information we're provided with in this case. We have 4 grams of calcium carbonate, 50 milliliters of 1 molar HCl. The number of moles of HCl will equal the 0.05 liters times 1 molar, which is 0.050 moles of HCl. How about the moles of calcium carbonate? Well, I go on the internet. Internet tells me that molar mass of calcium carbonate is 100.1 grams per mole. All right, well, how many moles is that? You take your mass of 4 grams and divide it by that 100.1 figure, and you get this right here. Now we ask, this is the key step right here. We ask ourselves, how much calcium carbonate do we need to consume all of the HCl? And this is the equation right here that's the heart of these kinds of problems. The number of moles of calcium carbonate there to consume all the HCl equals the number of moles of HCl times calcium carbonate per HCl. So when we do that calculation, we find for our acid, this is the number of moles of acid we have. For every HCl, there's just 1 calcium carbonate. So we find actually that we needed just 0.025 moles of calcium carbonate. Do we have it? Yes, we do. We do, and we know that because we have this much to start with. So we've got extra. We got more than we need. Now I think you can probably tell what's going to happen next, which is we're going to find that we have excess of one and the other is going to be limiting. If there's a limiting, there's going to be an excess. It's inevitable. By how much? Let's have a look. The number of moles of HCl to consume all the calcium carbonate equals calcium carbonate moles times HCl per calcium carbonate. So that's 0.04 moles times 2 HCl per calcium carbonate means 0.08 moles of HCl. And then we ask, do we have it? The answer is no, we don't, because we started with 0.050 moles of HCl, and we don't have the 0.08. This means that the HCl is a limiting reactant in this case. We just don't have enough of it to react with all the calcium carbonate, but we do have enough calcium carbonate to react with all the HCl. The next question that is often going to be asked is, by how much extra do we have? And here we do a simple subtraction problem. And here it is explored at the bottom right here. The extra calcium carbonate there equals the calcium carbonate that was available in the first place minus what was used. So in this case, we have the 0.04 moles was available, 0.025 moles was consumed by the HCl, means we have 0.015 extra moles of calcium carbonate left over. And where's our, well, here it is. In fact, it shows up really well here, doesn't it? See that? We've got this calcium carbonate that's still floating in the surface there, unconsumed. And if I try to shake it around, well, it's still reacting a little bit, but we have this cloudy solution. It's not transparent anymore because calcium carbonate is not soluble. So that's kind of evidence for that. If I was getting accurate reports of the exact concentrations, and I don't know that I am, I'm just going by what was in the cabinet and the exact composition, then the prediction is, well, how much? Prediction is that 0.015 moles of extra calcium carbonate. What's the mass of it? Well, it's 0.015 moles times the molar mass, again, 100.1 grams per mole, means that there should be floating around in here and on the surface, and I guess sunk to the bottom now, about 1.5 grams of calcium carbonate that never got used. So that's an example of calcium carbonate being a an excess reactant in that chemical reaction, and some evidence for it. There's also a handout that goes with today's lesson, and I'm going to go through, as I always do, a couple of questions from the handout to help you out. So the first one is, in question 1, we have a case where we've got hydrogen react with oxygen to make water. So I always like to write down what I know. I am told that we have 8.51 grams of H2 and 9.25 grams of oxygen. With that information then, we need to calculate chemical amounts, because in stoichiometry problems, you always start by calculating chemical amounts. We need molar masses for that. For molar masses, you're often going to find it really useful to just look them up on the internet. You can calculate them by hand if you want, but if I want to know the molar mass of some more complicated compound, I just type in the molar mass and say calcium carbonate, and it'll tell me right away. For oxygen gas, the molar mass is 32.0 grams per mole. For hydrogen gas, H2, is 2.02 grams per mole. We need that. How much hydrogen do we have? 8.51 grams divided by 2.02 grams per mole is 4.21 moles of H2. How much oxygen? 9.25 grams divided by 32.0 grams per mole means we have 2.89 moles of oxygen. Now we go through this and we ask, do we have enough H2 to react with all the O2? Do we have enough O2 to react with all the H2? One of them will be excess, the other will be limiting. There's only 2 reactants. If we have one, we're going to have the other. So let's see. How much H2 do we need to consume all the oxygen? And here again is the heart of any excess limiting reactant problem. The number of moles of H2 equals the number of moles of O2 times the H2 needed per O2. And I get for that 0.289 moles of O2 times 2 over 1 is 0.578 moles of H2. Oh, by the way, how did I get that? Sorry, I should have mentioned. We have 0.289 moles of oxygen. That figure went right here. So we're taking that and multiplying it by 2, and we find out that we need that many moles of hydrogen to consume all the oxygen. And then we ask, do we have it? We certainly do, because we have 4.21 moles of hydrogen gas. So we already know that oxygen is going to be the limiting reactant in this case. By how much? Again, well, for this one, we say the number of moles of oxygen needed would be number of moles of hydrogen times oxygen per hydrogen. It's 4.21 moles of hydrogen times the 1 oxygen per 2 hydrogen is 2.11 moles of oxygen. Sorry, I should have put a 2 right there. So that is dividing by 2, and that's how we get. That's how much oxygen we would need. Do we have it? No, we don't. We only have 0.289 moles of oxygen, so we're well short on the amounts of oxygen. That makes oxygen the limiting reactant. The next question we ask, because this is usually a question that gets asked, is how much is H2 in excess by? Again, we do this subtraction, a simple subtraction problem. The H-Tech2 is in excess by H2 available minus HC minus H2 used. HCl used. It's 4.21 moles minus 0.578 moles, and I get 3.63 moles excess of H2. The excess mass of hydrogen is going to be that 3.63 moles times 2.02 grams per mole means 7.34 grams of H2. In other words, 7.34 grams of hydrogen just escape into the air because they never get burned. All right, question 5 is the other one I wanted to review for you guys. Here's the question. This is a reaction that you actually saw in the types of reactions lab. The neutralization reaction involving sodium hydroxide and hydrochloric acid. A very simple reaction, and one that's actually really handy for stoichiometry. It's a good starter stoichiometry problem because the molar ratios are 1 to 1. You don't have to worry about them, although I'm going to put them in here. Here's the information we're given. We're told that we have 12.5 grams of hydrochloric acid, of the actual compound hydrochloric acid. Normally, this is going to be given to you as a volume and a molarity. Here, they just tell you straight up how much of it you have. We have 12.5 grams of sodium hydroxide. In stoichiometry problems, we always start by calculating chemical amounts. All right, how much have we got? For HCl, we have 12.5 grams divided by 36.46 grams per mole. You can calculate that from the periodic table, or you do what I did, just find it on the internet, the molar mass. We get 0.343 moles of HCl that we have. How about NaOH? It's 40 grams per mole. We have 12.5 grams of it. 12.5 grams divided by the grams per mole gives us 0.313 moles of sodium hydroxide. Given that the molar ratios are 1 to 1 to 1 to 1, you can probably see where this is going. So for B and C, I've answered them kind of in a packet right here, right? Because this was the answer for, these are the answers for A. For B and C, well, where are we at? The number of moles of NaOH to consume all the HCl equals what? Well, it's going to be moles of NaOH equals moles of HCl times NaOH per HCl. Well, that's 1. 0.343 times 1 NaOH per HCl is 0.343 moles of NaOH. We don't have it because we only have 0.313 moles of NaOH. How about HCl? How much of it do we need to consume all the NaOH? Well, the amount needed is HCl needed equals N of NaOH times the HCl per NaOH is 0.313 moles of HCl right there. And we do have it. We have enough HCl to use up all the NaOH. Hey, by the way, the excess, what is the excess? That's simply going to be the difference. The 0.343 moles of the HCl that's needed, the 0.343 moles that's available minus the 0.313 moles that's actually used gives us an excess of 0.030 moles of HCl. And you can express this as a mass if you want. You take the 0.030, multiply it by the 36.46, because that's the molar mass of HCl, and you get 1.10 grams. At least I do. I saw an answer key that said 1.06 because they were using different molar masses. And I think the thing that they were actually doing in that answer key, to be honest with you, is I think they were rounding off before they got to the end of the question. That's something you should avoid doing. So the next question is moles of NaCl that are formed. This is part D right here I have in the center of the screen, equals the moles of NaOH available times the NaCl per NaOH. In other words, what I'm saying is the amount of sodium chloride that gets made is going to be determined by the amount of sodium hydroxide that there is available to make it in the first place. There is going to be extra HCl left over, but what determines how much salt gets made, is the NaOH. How much then? Well, I did this calculation from the ground up. I said the moles of NaCl equal to 12.5 grams, what we have, divided by 40 grams per mole of NaOH, times 1 NaCl per NaOH is 0.313 moles of NaCl. Because the reactants are all, and the products are all in a 1-to-1 ratio, you probably didn't even need to see that. But it's good to do the calculations again from the ground up, because then you don't make these rounding errors along the way. Molar mass of sodium chloride, ask the internet, it'll tell you. It's 58.44 grams per mole. How much sodium chloride gets made? That's going to be the moles that are made multiplied by the molar mass, gives us 18.3 grams of sodium chloride. So in that reaction, we're combining 12.5 grams of HCl with 12.5 grams of NaOH, and our yield in that reaction is 18.3 grams of NaCl, and then there's some extra HCl that's not used. So that's what I want you to know about limiting and excess reactants. There are lots of examples, obviously, in your reading and other videos you can check out, but I hope you find these useful, because these are the answers for questions 1 and 5 in your assignment that I'm going to post shortly. Thank you.